So in the earlier video, we had studied about the transducer action of active transducers. In this video, now we are going to talk of the passive transducers. Like I had told you in the earlier video, that passive transducers are those which do not create or generate a new form of energy or an electrical signal. Rather, they modify or they control the existing voltage or a carrier signal. That means to design a passive transducer, we have an electronic circuit which already has some voltage or current flowing through it. It has a battery attached to it, and some element of that particular circuit is actually sensitive towards the physical parameter that I want to measure. For example, if I talk of pressure, or maybe I take the example of, say, temperature. So if I have to design a passive temperature transducer, so what I have to do is I need to have a circuit which already has a battery. It has some voltage flowing through it, some current flowing through it, but the circuit needs to have some device which is sensitive towards temperature. So as the temperature changes, the value of that particular component will vary, and as a result, there will be a variation in the voltage that is flowing through that circuit, right? So that is passive transducer. You're not creating an electrical signal, but you're modifying an existing electrical signal, right? So passive transducers, they utilize the principle of controlling a DC voltage or an AC carrier signal. And the transducer, it consists of some passive circuit elements which changes its value as a function of that physical variable which is to be measured, right? Physical variable, when I say, it means temperature, pressure, velocity, sound. These are all physical variables, right? And circuit elements is like passive elements. We have three passive elements which we are going to talk about in this session. That is resistor, capacitor, and inductor. These are circuit elements, that is electronic circuit elements. Okay, so now the idea of designing a passive transducer is that we need to design a circuit which has already some voltage and current flowing through it. It consists of passive elements, that is resistor, capacitor, or inductor, and these capacitors, resistors, or inductors, whatever we are using in the circuit, is actually sensitive towards that particular physical parameter which we want to measure. If it is pressure, then the passive element that we are using should be sensitive towards pressure. If it's temperature, then the passive element that you're using should be actually sensitive towards the temperature that we have to measure, right? So this is how we design the passive transducers. In this particular video, we'll be talking first of all about the passive transducers using resistive element. Resistance, all of you know. In your earlier classes, you must have studied what a resistance is, right? We all know what is a resistance, right? So any resistive element that changes its resistance as a function of physical variable can be used as a transducer for that variable. So if I have to design a resistive passive transducer for measuring temperature, I need to have an element whose resistance changes with respect to temperature. If I have to measure pressure, the resistive element that has to be used should be sensitive towards pressure. If it is force, it has to be sensitive towards force. So the idea is I need to use some resistive element in my circuit which is sensitive towards that particular physical or the physiological variable that I need to measure, right? So for example, a linear or a rotary potentiometer can be used to convert linear or rotary displacement into resistance change, right? Potentiometer, you all know, potentiometer is a device which has a range of resistances. Okay, it is a variable resistance. Okay, then similarly, resistivity of a conductive material sometimes is actually a function of temperature. There are certain substances out of which if you make a resistor, they are very sensitive towards temperature. That means if the temperature rises, as the temperature rises, the value of that resistor, it changes. So that property can be actually used to design a resistive passive transducer for temperature variations, right? So here you can see in the figure, this is an example. In figure A, you can see we have a linear potentiometer. The resistive element that you see with a tapped arrow in the center, This is actually a linear potentiometer, and the stab that you see in the center can actually be moved up and down. So any linearly moving device in your circuit or in your field can actually be connected to this tap. As there is a movement in that particular element, this tap also moves up and down, and as it moves up and down, the resistance, effective resistance which is there in the circuit actually changes. Okay, so actually also as the resistance will change, definitely the output voltage which is being shown in your voltmeter, that will change. So that means a linear movement that is taking place is giving you a corresponding change in the voltage of the circuit. So over here now you see that there is already a voltage existing in the circuit. We have a battery. Of course, the resistive element will work only if we have a battery attached to it. So if there is already a battery attached to it, there is already a voltage flowing through the circuit. The linear movement that takes place, it only changes the value of the resistance that is a part of your circuit, right? So what happens, that change in resistance will actually give you a fluctuation in voltage. So already existing voltage has been modified or controlled by in correspondence to the linear movement that was taking place. So what we have done is, there was a mechanical movement, that is linear movement. Displacement, you can say, that is a mechanical movement that has been controlling the output voltage of this circuit by changing the effective resistance of the circuit, right? So similar thing can be done for rotatory displacement also. You can see figure B. This is a potentiometer which is round in structure. If there is a rotatory angular movement taking place, you can connect it to the sliding pointer, and as your displacing element moves, by the same angle the pointer will move, and the effective resistance of the circuit again changes, and that will give you a fluctuation in the output voltage, right? So you can say that this is one of the examples where you can correlate the physical movement, displacement, either linear or rotatory, to the output voltage changes. Okay, so in all these circuits you can see that we are not creating a voltage, we are simply changing or modulating or controlling the existing voltage of the circuit in correspondence to the change in the physical variable. Over here, physical variable is movement, displacement, either linear or rotatory, and the output that we are getting is change in voltage, right? So this is one example of using resistive element for measuring displacement. Another possibility is that you can have photoresistive elements. Photoresistive elements means that these are devices or materials which are very much sensitive towards light. As the light rays, they fall on the element, the electrons, if they break open, the resistivity, of course, if the conductivity is increasing, that means resistivity is decreasing. Resistance will increase, only then the conductivity will, if the resistance will decrease, only then the conductivity will increase, right? So there are these, this is also one of the phenomena which we can use, like for detecting the intensity of light, right? So you can have devices or sensors designed for measuring the intensity of light or the reflected intensity of light with the help of resistive elements. This is also one of the phenomena which, with the help of which, you can design the resistive passive elements. Okay, now when we talk of this resistive element, the most commonly used sensor that we use in a very, very wide range of biomedical applications is a strain gauge. Okay, so most transducers used for mechanical variables utilize a resistive element called a strain gauge. Okay, so strain gauge is actually a resistive element, okay, whose resistance is actually a function of shape, right? It is a strain gauge is a resistor that is used to measure strain on the object whenever an external force is applied, due to which there is a deformation taking place in the shape of the object. The deformation could be either compressive force or a tensile force. We call it a strain. That means when you have an object, okay, of a specific geometry, when you apply certain force on it, maybe a compressive force, maybe you are compressing that particular object from two sides, or maybe a tensile strength or a force that is just trying to stretch that object, there will always be a strain developed in that particular object. So the that strain that is developed in that object is actually measured with the help of a strain gauge. Okay, when an object deforms within the limit of elasticity, either it will become narrow or it will become longer. Okay, narrower and longer, or it will become shorter and broad. So as a result of these changes, there is a resistance change in that particular element. Okay, so a strain gauge is actually sensitive to that small change, the changes that occur in the geometry of the object. By measuring the change in resistance of that object, the amount of induced stress is actually calculated. So things will be more clear with this example. Here at the bottom of the slide, you can see there is a cylindrical shape object. Okay, now consider this cylindrical shaped object as a resistance. So we have a resistive element which is cylindrical in shape. It has length L and it has a cross-sectional area capital A. And the resistivity of the material is denoted by R. Right. So this particular geometry will have some inherent resistance of its own. That means if I put this element into an electrical circuit, it will act like a resistor, right? And the value of that resistance which it is going to offer to the circuit is actually small r multiplied by L by A. L is the length of the element and A is the cross-sectional area. Right, so this is in the normal condition. Now what I do is I apply certain force on this particular element. In the figure you can see denoted by F, there are two arrows. I apply an axial force or a tensile force. That means from both the sides I hold this element and I try to stretch it within its elasticity limit. Right, now when I stretch this element, what happens? There is a length increase and decrease in the cross-sectional area. So the length will actually increase by say small amount delta L, and the cross-sectional area will decrease by a small amount delta A. This change in the geometry will actually result in a change in resistance. If you see the formula over here, this capital R formula, if you see, it is directly proportional to capital L but inversely proportional to A. So if I say that after applying a force F, L has increased and A has decreased, that means the net value of resistance will actually increase. Okay, so if I was using this element in my circuit, it was giving me some resistance R, and correspondingly I can measure the voltage, suppose V, in that particular circuit. Now when I apply this force, when I stretch this element, there is a change in the length and area which actually results into an increase in resistance. So corresponding change will be reflected in the voltage of that circuit, right? Similarly, if I apply this stretching force in a vertical manner, that is from top to bottom, if I try to stretch it, what happens? The length will decrease and the cross-sectional area will actually increase. Now this will result in an inverse effect, that is the resistance will actually decrease. Okay, because from the formula we can see resistance is directly proportional to length but inversely proportional to area. So if length decreases and area increases, the resistance will decrease. So that will again show a corresponding deflection in the voltage of that particular circuit, right? This is the fundamental of a strain gauge. So strain gauge is actually made up of an element, resistive element, whose resistance is very, very sensitive towards the geometry of that element. Okay, even a slight force when it is applied to that element, the geometry changes and correspondingly the resistance changes. Okay, so in the figure you can see over here, this is what a strain gauge actually looks like. Now, this device is actually designed for, measuring a very, very, very small change of geometry, resulting in a very small change of resistance. So sometimes it so happens, suppose I use a simple single wire, right, to measure this particular change in resistance. The resistance change will be there, but the value that will change will be so small and so feeble that it will be very difficult for us to use that value in the further circuits. So in this you can see the strain gauge that you are seeing over here. It has multiple parallel zigzag lines. These are actually zigzag pattern of a wire. So whenever this particular component is stretched from both the sides, all the wires, they stretch equally because they are all parallel lines. So they get stretched equally, and the change in resistance or the effect of that force is actually same in all these, right? So that net amount is considerable enough for us to actually use it in the circuit, right? So this particular small it looks like a small chip kind of a thing. It is actually implanted on whatever area where we want to measure the force, or wherever we want to measure the deformation, right? So what we do is we implant the strain gauge on that particular surface. As that surface stretches, or if that surface bends, these wires, they also stretch or bend correspondingly. And when that geometry change takes place in this particular element, the net resistance of the element changes, and correspondingly it gives us a change in the voltage of the circuit, right? So the ratio of the resulting resistance change, that is delta R by R, to the change in the length, delta L by L, is called the gauge factor. And usually in metals, the gauge factor ranges is about 2, and for silicon it is about 120. So it actually depends upon the requirement of the particular application, that what gauge factor value we want to select, right? So this is how we can actually use a resistive element which is sensitive towards a particular kind of physical phenomena, and use that resistive element in a circuit, right, to design passive transducers.